Okay, question 51. Which can lose a proton more readily? Methyl group bound to cyclohexane over here on the left, or methyl group bound to benzene over here on the right? Again, this is a chapter about resonance, so delocalized electrons are key and are king. So try to compare the benzene to the cyclohexane. Try to see what's obviously different about the two. And we're going to try to relate how we can have electrons move for both of these structures. So the obvious thing that's different here is that for the cyclohexane, we don't have 3 pi bonds, whereas for the benzene, we have 3 pi bonds. So thinking about also what we're trying to compare, it's asking you which can lose a proton more readily. Okay, and as soon as you read that statement, a term should pop in your head immediately that we talk about a lot, and it's going to be pKa. So acidity of a compound, or the propensity of a carbon or an atom or a molecule to lose H plus, okay, to lose a proton. Okay, so what we're going to do is go ahead and lose a proton from one on the left, one on the right, and compare and contrast the stability of the resulting negatively charged species. Okay, so let's just say we lost a proton. Okay, so we're going to lose a proton from this guy. Okay? So if we lose a proton, we'll put it on this carbon right here, and we'll do the same thing for this carbon right here. Okay, so I'll draw the results if we lost an H plus. Okay, and if this makes it easier, or if it makes it more palatable for you, you can imagine some base. Okay, just a random base coming in to deprotonate. Okay, if that makes it easier for you to see. Either way works, doesn't really matter. What we're comparing is not the H plus. What we're comparing is the final product. Okay, so let's go ahead and redraw both of these guys down below. And I'm just going to cut and paste because I can do that, and I'm slightly lazy. So what we're going to do, get rid of this, and we will draw negative on both of these carbons. Okay, so let's draw a negative on this carbon and a negative on this carbon. And so basically, the ability of both of these molecules to lose this proton or this H plus, the ability for the molecules to lose that H plus is directly proportional to the stability of the resulting base. Okay, because the top molecule is acting as an acid, and the bottom molecule is acting as a conjugate base. Okay, so the more stable this conjugate base is, the more farther to the right, or the farther down in this case, we're going to go for equilibrium. Okay, because remember, this isn't a one-way street. We can go back and forth and back and forth and back and forth. Okay, so again, HA and A minus. Okay, so again, since we're talking about delocalized electrons, this is what the chapter is all about. The question you should ask yourself is, well, is there any difference in the stability of this negative charge versus this negative charge? And indeed there is. There's a huge difference in stability. So thinking about resonance, can we actually draw resonance for this molecule on the left versus can we draw resonance for the molecule on the right? The answer is, for the molecule on the right at least, yes. Yes, we actually can draw resonance. So we can draw a resonance form like so, and we can redraw this guy like this. Negative charge on the bottom carbon, and we can draw a double bound carbon right there. And hopefully you can see that you can take this negative charge and you can push it all the way around the ring if you really wanted to. Okay, so remember now, well, hold on, let's go back to this other molecule on the left. Can we actually draw a resonance for this molecule on the left? Can we actually do the same thing? Well, thinking about, what kind of structure we have, if we tried to do the same thing, what we would get would be this molecule on the left. We would have this hydrogen, two bonds, so we have a pi bond, and we have 2 hydrogens here. So thinking about this carbon right here, we have a carbon with 1, 2, 3, 4, 5 bonds to it. And so that means we're breaking the octet rule for this carbon in the yellow, and that means that we can't actually put electrons on that carbon-carbon bond. Okay, so this actual electron push is completely wrong. It's no good. So let's go ahead and get rid of that resonance arrow. And I'll mark this wrong, give it a frowny face, plus 0 points for this person. Okay, so thinking about that, so plus 0 points. What you can say for the molecule on the left, at least, is that the molecule on the left has no resonance, and the molecule on the right has at least 1, 2, 3, 4, 4 resonance structures. Okay, so you can draw 4 different resonance structures. Okay, so what you're comparing and contrasting now is stability. So thinking about stability, going back to our concept over and over and over again of nature hates an excess and nature hates a deficit. So in this case, we're dealing with an excess. We're dealing with an excess right here with this negative charge. We have an excess of electrons. So since nature hates an excess, anything that we can do to disperse that electron density throughout the molecule is going to, reduce the stress on this carbon. So we're going to disperse the electron density. We're going to make nature a little bit happier by having not so much of an excess, not so much of a deficit. We're going to try to have this nice middle neutral ground. Okay, because remember, none of these resonance forms are indicative of reality, but they all contribute to what is reality. Okay, so you have 1, 2, 3, 4 different possible structures that are none of them are real, but altogether they give you a good impression of what reality is like for this negatively charged compound. Okay, so again, this is extremely negative, not very happy. This is not so negative. This is more towards neutral. So this is going to be extremely stable. Okay, so because this molecule on the right is extremely stable, it's going to be this molecule up top, or this HA, is going to be the molecule that will lose that proton more readily. Okay, so this molecule is most acidic. This molecule on the left is least acidic. Okay, all right, cool. Overall, not too terrible of a concept in terms of pushing electrons around. The kicker here for most people seems to be understanding that resonance is a stabilizing effect, and that stabilizing effect has a direct impact on acidity. Okay, so once you get that, you're good. All right, next question.